Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Travis Rector, Lisa Prato, and Ronan Kerr with us today. Hello, all.
Hi, how's it going?
Good, good. Ronan, let's start with you. What is your geolocation?
I'm currently in Toronto, Ontario, Canada.
Okay. And it is July 14th of 2025 as we record this. And how is summer in the far northern reaches?
Honestly, quite nice right now. We got some nice sun outside. We had a little bit of smoke filtering down from the wildfires
Oh,
up in
okay.
northern Canada, which is not the best, but overall, it's been a fairly pleasant summer so far, and it's been kind of hot lately.
Very cool. Very good. I understand you just came back from some wonderful trip in Europe.
Yeah, exactly. I was actually just over in Ireland. That's where the European Astronomical Society was having their
Yep.
annual meeting, and I went there, presented some of the work that you're going to be hearing about today, at least to some degree. It's a bit of this and a bit of stuff from a different paper, but presented that, heard some great science from other people doing research in the field, got some new ideas, a couple more papers that might be coming out soon, hopefully.
Cool.
So yeah, I think it was quite productive. And then I got a like 4 days to go around the southwest of Ireland and you know check out some beautiful landscapes. That was pretty cool.
Very nice. Cool. Travis, how about you? What's your geolocation?
Hi, I'm in Anchorage, Alaska. Currently, so we're even further north. Yeah.
Yeah.
Currently experiencing a heat wave here. It's about 60 degrees Fahrenheit.
Oh, yeah, you're right, yeah. Brr. I was
So,
just in Alaska. I think God, it was maybe all of us were. I don't know, but I was just in Alaska for the AAS meeting up there, and it was beautiful, really nice.
yes, we had wonderful weather. First 2 days were kind of rainy, but then
Mhm.
we had spectacular weather
Yeah,
thereafter. So it was nice for Alaska to show off for our visitors.
yeah, it was very cool. It was a wonderful time. Very good. And Lisa, what's your geolocation?
Well, so I'm not as far north as my colleagues, but I am higher off the average surface of the planet because I'm in Flagstaff, Arizona,
Ooh.
7,000 feet above sea level.
Very
And
cool.
it's really hot and it's really smoky because the
Oh,
yeah,
please, it's
North
hot.
Rim burning,
Please, it's hot.
which is not
Oh no.
fun news, but yeah, I've just had a couple great weekends and I'm excited about this project.
Very cool. Very nice. And let's see, let's go around one more time. We'll go in reverse order. Lisa, what do you like to do for research?
Oh, young stars, young
Young
binary
stars.
stars, potential for planet formation in young binaries, circumstellar disk evolution in binaries, and the potential well, actually, the process of how do planets form generally, not just in binaries, but around singles. So I look for one part of my science is looking for the youngest generation of planets, newly formed planets
Very
around young
cool.
stars.
Very cool. Travis, what do you like to do for research?
Well, there's quite a few different topics that I work on. I started originally in AGN jets,
Ah,
now step down to the smaller scale of Herbig Haro outflows. And
hey.
for seeing a Herbig Haro object, you know why they're so interesting. They're some of the most objects out in the universe. And so it's been a real treat to work on that as well.
I appreciate those spatial skills between AG and Jets and HHs. Very good. And Ronan, how about you? What do you like to do for research?
Yeah, so I'm also into young stars, but I particularly like to use them as a sort of a record of the star formation history of the galaxy.
Ah,
So,
okay.
when star formation happens, it leaves behind stars after the gas disperses, and you can use those stars to sort of reconstruct the gas and do this wonderful long-term record of star formation in a region, be it like locally or in the galaxy more broadly. And of course, this dovetails really well with work from Trappist and Lisa, who are studying various different scales of star formation. This gives you a lot of information about the broader context of that. And I think that's going to you know segue pretty well into what we're doing in this project here.
Very cool. That is an awesome collection of talents on this. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. The Herbig Haro outflow content and star forming environment of Circinus West and East. And Travis, Lisa, and Ronan, take us away.
All right. So I think the genesis of this work was some imaging that Travis had done, and he'll talk a little bit more about that himself. But he had seen some Herbig Haro objects in star-forming regions, and I had worked on some of the regions he looked at, and so we started collaborating on this work a few years ago. And Circinus is a very interesting region. There's east and west, these two clouds next to each other.
Okay.
And so we started looking for the Herbig Haro objects. So I'm going to give sort of the overview of why is this interesting at all. And this is a relatively new field for me. I just because I work on young stars and their disks, I hadn't actually moved into working on jets. But let me talk a little bit about what a Herbig Haro object is. It's co-named for Guillermo Haro and George Herbig. In the early 50s, both of them were working on the spectroscopy of these unusual objects, trying to understand what they were. They had all these emission lines, and so they went ahead and eventually they communicated, and these objects were named after both of them. And it's fascinating because it represents a very specific stage in star formation, and it's dependent not only on the stage of star formation, but it's also dependent on the ambient region. If you have gas in a molecular cloud in a region where there is a young star. So we have core collapse in giant molecular clouds, and this generates these protostars, collapsing protostars. And at some point, you have with the angular momentum. Angular momentum in some particular direction. You have the spinning star. So you end up with your circumstellar disk, but the interaction between the accretion from that disk and the star generates these jets. And Travis can speak to these a little bit too, since he's a specialist in AGN outflows and jets. But we have these very energetic jets. They can have velocities of hundreds of kilometers per second.
Yeah.
And the interactions between the jets and even material entrained in the jets moving at slower velocities. You can have a higher velocity jet impact these sort of clumps of slower velocity gas in the jet. And so you can actually create these sort of Herbig Haro objects along the jet, and then when the jet impacts some ambient medium.
Yes.
And so we have these Herbig Haro objects with a variety of morphologies. The classical is with the bow shock.
Yeah.
And so you see you see shocked gas, you'll see ionized hydrogen recombination, you see sulfur 2 forbidden emission. You'll see in the infrared, you'll see the quadrupole emission from molecular hydrogen at 0.12 microns, and so they're fascinating. There's these great objects, but they're big. And which is very, very nice. So they can spread out over parsecs. And so you can actually see these objects. You can see this shocked gas when you can't necessarily see the embedded star.
Yeah.
Star that has or T-Tauri star that is actually creating this jet. And so it's a very, very short-lived phase. But when you see it, it's this big red flag that there's a young star, that there's star formation ongoing. And so it's a great way to look at regions and to assess the sort of star formation stage of a region. Only the problem is in part that you can't necessarily see through the optically thick cloud to see all of the embedded stars and all of the Herbig Haro objects. But if you can detect many of them, then you have some sense of, it's like a chronometer of where that region is. And
cool. Yeah, cool.
Yeah. And so our idea was to sort of use these to sort of age state different regions, or to at least say this region is active, this region is active. There's other regions, and we can talk about them a little bit later, but regions, massive amounts of gas. I mean, hundreds of thousands of solar masses of gas that were not well studied for various reasons, and you can actually pick out these Herbig Haro objects. And so they have Temperatures are thousands of, 8,000, 10,000, 12,000 degrees. Electron density is 10 to the 2, 10 to the 3 inverse centimeters. And there's not a lot of gas entrained in these outflows, but it's just makes a big impact. It's kind of like, from my point of view, it's sort of like when you're studying young stars, like how do you know what's a young star? You can see its circumstellar disk really easily because there are many AU, tens of AU, 100 AU. You can see the disk, and that's really easy. With the Herbig Haro objects, they're parsecs. They can be parsec scale. So it's a great like giant thing in a star forming region that flags up age.
Nice.
And so this paper in particular, we were looking at Circinus East and Circinus West. And previous work has been done on Circinus West, identifying some Herbig Haro objects there. And we went back with sort of more sensitive imaging, and Travis can speak to this a bit, but we found more objects. We had a paper a few years ago. We had found some more objects in Circinus West. And we went back with a combination of telescope and instrument that really increased our sensitivity. And we got both fields, Circinus East and West, with higher sensitivity. And lo and behold, we found Herbig Haro objects in Circinus. Yeah, which has never been done before. So we have identified the first Herbig Haro objects in Circinus East.
Congratulations.
And, thank you. It was pretty cool because questions, are they the same distance? Are they related? They look very, very different. The two regions, the morphologies are extremely different.
Here we go.
So here's one from our paper. You can see on the right-hand side is Circinus West. And look at how the morphology is very filamentary. There's like these fingers. So there have been some papers written about, potential sources of star formation, triggers for star formation in that region. And could it be, these are the reasons why we see so many Herbig Haro objects here. But look at the Circinus East, totally different. There's hardly any of that filamentary structure. It's nebulous. It's covers these are, by the way, these are the footprints of the camera we use, DE cam, on the Blanc telescope. And our previous paper, you can see the blue square on the right. That's the previous field of view we looked at with a different telescope. These
very good.
Are exactly the same. They're both about 3 degrees in diameter. So I love this combination of instrument and telescope. Props to Noir Lab. Because
what's the difference, or what's the spatial difference between East and West?
You are seeing exactly the same size field in these two figures. And so it's 3 degrees across. And so roughly, I don't know, West is, it's filamentary, so it's kind of hard to say, right? But it's
exactly
3 across at most. In East, it's hard to tell, right? Because that kind of fuzziness, like, sort of fades down to the lower right there. But very different morphologies, very different frequency of Herbig Haro objects. And so we're like, is East younger? Is East older? Did it already?
Good question.
And so, and so we found in the appendix of our paper, we had a little analysis about distances to the two regions. And they seem to be the same distance, roughly.
Let's pop down. Let's take a look at that appendix real quick. Distance to the embedded stars. Okay.
Several hundred parsecs. So we've got, on the order of 800, say, to both of them. So, for astronomy, that's pretty good.
All right.
So they're the same distance, maybe they're the same age, but I would love to have Ronan or Travis come in here because it's because of Travis's imaging techniques that we were able to identify these faint things at all. Cool. And Ronan has more to say about the distances and the distributions.
Yeah, sure thing. So I could try to jump in a little bit here. So what we did find here was that both populations had distances that were quite consistent with each other.
Yeah.
Now, I will hold off a little bit here because we actually go into substructure within one of the regions, and
Okay.
that ends up being important later on. But for the time being, it looks like Circinus West might be a little bit closer than Circinus East, but they're all within the same rough region that they are fully consistent with being, part of the same initial gas cloud. It's quite
Yeah.
frequent that we see,
Okay.
you
Okay.
know, structures that are 30, 40 parsecs long. I think we're consistent with that in this case. So what it does mean is that they're far enough apart that we might see different environments in each. That ends up being very important later on when we start discussing the interaction between each of these clouds and the parent environment.
Good. I'm with you. Okay.
All right. So I think
Let's slide on up then. We were
I'm
just
back up.
figure one and onwards.
Travis, do you want to take it away?
Sure. So let me talk a little bit about how we actually did the search.
Okay.
First off, I mentioned Herbig Haro objects are quite rare. There's only about 1,200 of them known in total, which, compared to most classes of astronomical objects, that's extremely rare. So why is that? Well, part of it is they're hard to detect.
Okay.
These are objects that, as Lisa mentioned, are sources exclusively of line emission from the collisionally excited shocks.
Yeah.
And they're also seen, as you can see in these two pictures, seen in rather complex environments where you may also have a particular H alpha emission just from the existing nebulosity. So prior searches for HH objects, they'll also mention because they're faint. So prior searches of HH objects have been somewhat limited because you needed to make a trade-off. You either had a large aperture telescope with good sensitivity but a small field of view,
Okay.
or a smaller aperture telescope where you have just the opposite. And so there's two major advances that have really enabled us to search for HH objects so effectively. The first is just the instrumentation. As you can see in these two pictures, the field of view of DE-CAM is just huge. It's a 520 megapixel camera, which
Yeah.
up until recently was very impressive. Ruben
Ruben
has made it
smoked that.
small now, but still a very big field of view. So you have subarc second pixels over a 3 square degree field of view. So just massive. And the one thing that DE-CAM has that Rubens does not is narrowband filters. So we do have H alpha and sulfur 2 and other narrowband filters
Yep.
aid us in the quest. The other big step forward is just simply how we do the search, and that is creating color composite images that allow us to find these HH objects. Prior searches tended, at least in the optical, tended to rely on, say, like looking for sulfur 2 narrowband imaging and then compare it to a continuum image and then looking for sources that are in the sulfur 2 image but not in the continuum. So it's just kind of an eyeball search.
Mm-hmm.
And so what we've done here, though, is to create a color composite image first using H alpha narrowband and then a broadband G and I, Sloan G and I.
Mm-hmm.
And what that does is it shows you where you have continuum sources and where you have just line sources. And in particular, those two broadband filters also show you the dust. They show you the density of the dust. It shows you the color of the stars. And so it allows you to see the image, the star forming region in more detail. And so what we do is we first create a color composite where we have H alpha as a red, and then we have the broadband filters of I as an orange, and then blue. The G band filter is blue. And so what we're doing is we're looking specifically for sources that are a deep red, which indicate that they're only a source of line emission. And then when we find these sources, we do follow-up observations in sulfur 2 to confirm that they are indeed collisionally excited shocks from Herbig Haro outflows. And we've had tremendous success with this technique. Prior to our searching, there was only a handful of these objects known as Circinus West. We now know of over, I think, 60 of them, something like that, around 60. And then in Circinus East, where none had been seen before, we found 9. And so Really, the advantage that we have here is the tremendous field of view and the subarc second resolution and narrowband filters of the DE cam on the Blanco 4-meter telescope, and also using this color compositing method, we've been able to find in these regions and in others scads of these Herbig Haro objects.
Cool. So let me ask a trivial question. So we know about 1,200 of these things. How many have you found?
We have not just in these regions, but other regions as well. We have found over 200.
Phew, awesome.
And
One fifth.
so, just think back to the 1950s to the present.
Mm-hmm.
But and again, I want to emphasize this really is a credit to the instrumentation that we have access to.
Yep.
We have toys that prior astronomers did not, and so we've been able to do some really remarkable stuff with them.
Go tech.
That question, Frank, makes me want to make a plot of discovery of Herbig Haro objects as a function of time. And I think
Yes.
it would like spike up
Doop.
in work we've been doing just in the last, what, Travis, 3 or 4 years with DE cam.
Yeah, and this also raised some interesting questions because I mean, when these objects are numbered sequentially from their date of discovery.
Okay.
At first, they were because they were just, when they were first discovered, they were sort of these discrete sources. And now we're finding these outflows that have many components to them. And so there's some ambiguity as to how these objects should be numbered and named because
Ooh.
you may have numbers that are very different from each other
Ooh.
that are part of the same outflow.
Mm-hmm. Mm-hmm. Well, let's hope if it does that there's some sane terminology or taxonomy for them. Unlike type 2 supernovae, but that's another topic. Onwards. Very cool. Very nice. I'm with you.
Okay, so I think, as Lisa's already mentioned, the morphology, and if you want to go to the next figure, I think it shows us.
Yeah, let's take a look. Okay, well, check all these out, people. Newly discovered HH objects.
Yeah.
Woohoo! That is
And you
awesome.
can see in the numbering there, we did find additional components of previously known outflows. So HH76 is one of the, as you can guess from the low number, is one of the early
Yeah.
outflows discovered in this field, and we discovered additional components to it. And a sort of tradition to
Oh,
to
yeah.
add letters to indicate that these are, just components of the same outflow.
I'm with you. Very
So we found a bunch of these, and in the next figure, I think you'll see, particularly for Circinus
Ooh,
West, just where these things are located.
very
The
cool.
the red and green circles show where the outflows are. The red circles represent previously known sources, the green new ones.
Okay.
And you can see that these follow along very nicely along the tendrils of this very disrupted region. And that makes sense because what you need is not only
Bang, 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 bang.
ISOs producing the outflows, but you also need them
Cool.
to be able to break out. And I think in comparison to Circinus East, we do see evidence of outflows there, but they're just barely visible. And I think the ones that we see reveal that there is a hidden population where the jets being produced just can't get out of the gas. And so it's sort of a sweet spot. You need to have the stars evolved enough that you are having these outflows,
Your breakout.
and you need the surrounding medium to be fragmented enough that these outflows can escape. And as Lisa mentioned, these outflows can extend many parsecs away. And so while we see most of these outflows along the edges, you can see them quite a ways away from these fragmented regions. So it is really remarkable how far out they can get once they do break out.
Does the size of the circle mean anything?
Size of the circle roughly indicates the size of the HH object
Got it.
itself. Some of
Okay.
them are larger, and it just reveals it. I mean, it's not just we're not just simply seeing components of the jet. What we're really seeing is
Yeah.
where the jet is colliding with its ambient medium. So it is the geometry and the size of these HH objects can be quite complicated. As Lisa mentioned, some do have sort of a picture perfect bow shock that is handy for indicating the origin of the source, but many have these very unusual shapes that really reflect more I think the shape of the gas that's being hit rather than the jet.
Right. Exactly. Cool. That's a beautiful image. Very nice.
Do you want to, if you go to one of the subsequent sort of postage stamp images, we have some examples of
Yeah, cutouts, right? That's what we call them.
Yeah.
Let's take a look
Yeah.
at some of these beauties.
When we say faint, we mean faint.
Yeah, so you can see here is just, the unusual shapes that you're seeing in
Oh.
some of these sources, like the components, the new components, HH76.
Mhm.
This is an example like the 76C and 76C2. The one on the left had been discovered
Okay.
before, but then our deeper imaging with the 4-meter class telescope revealed
Okay.
additional components.
Very
And
nice.
we have to be careful in the naming. We don't want to assume that these objects are connected just because they appear to be co-located in a two-dimensional image. But in many cases, we can piece together whether or not they are connected to each other.
Okay.
I
Very.
just want to point out that the grayscale is the sulfur 2, forbidden
Aha.
sulfur 2
Okay.
confirmation, and the reddish ones are Travis's filter combinations.
Beautiful.
So
Okay, a
the
little bit
GIA
here,
alpha.
a little bit over, a little there, and then here we got some new ones. Boom, boom. Okay, yeah, I see that. Ooh, what's going on here? That one got blown out a little bit.
They're just some charged bleeds, and it does reveal that these, as you can see in these pictures, these objects are located in very complex environments, and so it can be very hard to differentiate them. And that's I think where the way we use color, I think really helps us in that way
Hmm,
because these distinctively red blobs in the color composite images really pop out
they pop out at you, yeah.
in environments.
And I think we got a few more
I
down.
think one thing that's occurring to me as we're having this conversation is that in some sense we're sort of expanding the range of Herbig objects down to like some pretty small things. And yeah, I think we've known about the big beautiful ones or the bow shocks for many years,
Yeah.
but they're sort of pervasive maybe on these very small faint scales.
Okay.
And having something like DE cam with the multiple filters is just a phenomenal way to pick up these faint things. So this,
Nice.
sort of more general sense, this might be giving us clues to the sort of
This one.
very small sort of power jets that are
Yeah.
still driving these little ones.
Yeah. Very nice. Beautiful. Two of them. Okay.
There's some nice ones in Circinus East as well.
Okay, so I'm
I don't know which
still
figure number it was, but
6. This one is in west. Look at that red stick out. And there's kind of a sulfur 2 right there. We're
yeah.
doing good. Let's take a look at something from the east. Do 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 do. No,
Those are all still from the
West.
west.
but
Yeah.
red,
And
red,
these ones just happen to be adjacent,
red,
so
red, red. Very cool. Let's go down. Let's take a look at some more of these cutouts. And this one is a zoom this one out. Is that on the east? The
No, it's still
yeah,
West.
still
these are
west.
still west. It just so happens the ones we found in the east were adjacent to each other, so we just included them in a single larger picture. Yeah, here you go. So
Ah,
these
there we go.
are
Yep.
from the east, and this is a wonderful example where we see these two red Herbig Haro outflows that are coming from a source deeply embedded in the cloud. If you look in the infrared, you can see the progenitor. And but these outflows are extremely faint, and so it does speak to the importance of having aperture to find them.
Yeah.
And you can see a bow shock in this one on the sort of brighter
Okay.
end.
Okay. Yeah. Yeah.
Yeah,
Okay. I'll use my imagination on that one.
yeah,
Yes.
a little bit.
Good.
Well, there's a
Right there.
star in the way, but you can see it more clearly
Sure.
in the sulfur too, I think.
Yeah. Uh-huh. Uh-huh. Yeah, there's a bow shock. Okay. Very cool. Got it all. Okay.
So
I was gonna say,
the age has to be about 1 million years old because that's when a star reaches the stage at which it is driving the jet. And so Travis saw when we were writing this up, Travis saw Kerr et al. 2021 had done some studies of the kinematics of stars in the Circinus region, and that's the sister paper to this one. But
Hmm.
Ronan worked on a paper several years earlier, and Travis noted the reference and said, "Hey, Lisa, take a look at this." And Ronan's paper with his Gaia data said, "Oh, the Circinus region is 5 million years old." All right,
Huh?
it's 5 million years old.
Huh?
Let me shoot him an email and see what's going on here.
Okay.
Yeah, if the region really only does consider gas clouds with Herbig objects, that does make absolutely no sense. But turns out it actually doesn't. There's actually a lot more to it. And
Okay.
and you can sort of get a bit of a sense for this when you go back up to the sort of like wide scale picture that we showed you earlier on. So
Okay. Let's go to the
uh
full scale.
yeah,
This
way,
one?
way up.
This one? You want two or one?
Uh Not that. One.
One.
Okay, the color
One.
scheme. Yeah, yeah. I'm with
Yes, that's the
you.
one.
Okay. Okay.
Yeah. So, especially in the eastern region, you can see that there's this massive amount of emission to the upper left. And it turns out that that emission is primarily being driven by a very large cluster of stars that is connected to Circinus towards the upper left of the cloud here. So that's a little bit of a teaser for you. But let's go into sort of like the introduction of my material here. So let's zoom out a little bit here.
Yep.
And let's go to, I believe I've got a section on introducing the data set.
Here's the data.
So observations. Let's go down to I think it says like broader environment or something like that. It's got a label like that. I think it's like 2.2 maybe. Yeah,
Analysis.
here we go. Extended stellar population. Yeah,
Right.
that's the one. So no, yeah, went
2.3.
past it. Yeah,
Okay.
2.2.
Okay. I gotta go slower.
No, you passed it
2.2.
already.
We have bandwidth lag and I'm moving too fast. Okay.
Oh no.
There
All
we
right.
go. A little bit further up. It's on the right.
Oh, you're right. Sorry, it is 2.3. I apologize.
2.2.
Yeah,
Yeah, a
you were
little
right
bit.
there, Lisa.
Okay,
Here
there
we
you
go.
go. 2.3.
Good, perfect. All
5
right, yeah, there's
million
definitely a little
years.
bit of lag going on here.
5
But
million
yeah,
years.
so basically what happened was I had this data set from a paper that I published a couple of years ago. It's part of the SPYGLASS program, I call it. Stars with photometrically young Gaia luminosities around the solar system.
Uh-huh.
Basically what we do is we look at the data from Gaia and look, okay, are there any stars that are brighter than they should be for their color, right? So this
Okay.
is consistent with the star being on the premean sequence, which is, they haven't fully contracted into their main sequence size yet, so they end up being bigger
Mhm.
and therefore brighter. So we can
Yes.
detect those based on their photometry from Gaia, photometry combined with their distances.
Yeah.
So I basically found a bunch of these young stars, and then I clustered them into populations. And one of those populations was what I labeled as the Circinus complex. And the Circinus complex, for me, didn't contain just, Circinus West, Circinus East. It contained a whole bunch of stuff that had nothing to do with those two clouds.
Okay.
And it turns out that those sort of other populations are actually dominant, such that when I recorded 5 million years as the age of the region, it
Yes.
really basically completely like clipped out
Okay.
everything young and
Right.
basically just fit the older population that's also connected.
This is
But that
dominant.
older population is really important. So let's see, is there anything else we should discuss in this section here? I think this is more or less it for this section. I think we can go down to some of the figures where I introduce the broader view of the region. Yeah, this is more or less just describing the data
Uh-huh.
set
Uh-huh.
and saying how we down selected it. So I think we
Yep.
you know
Mhm.
had some cuts on membership probability based on both, how central it was in the velocity distribution and whether it was in the correct part of the color Mantoux diagram to be,
Sure. That was helpful. Yes.
identifiable as young. Because basically what we did in the Spyglass papers was we started by identifying young stars. We then looked for phase space neighbors around it. And the reason that you do that is because if you only look for the stars that are reliably identifiable as young, you're
Yes.
going to miss all the stars that have already gotten onto the main sequence.
Right.
So like any like FG stars, you won't detect those because those things are already going to look like a 100 million-year-old star or
Right.
in some cases a billion-year-old star. Well, maybe not a billion. Well, yeah, there are some cases where a billion-year-old star could look like
A
that.
factor of 10 in age. It's okay. It's good.
Yeah, exactly. You're getting the idea. So yeah, you want to include all these, populations around them.
Absolutely.
And when you include the phase-based neighbors, you get a whole bunch of stuff that is not related to your region, so you got to click those.
Okay.
So that's basically how the assembly of the data set worked.
Okay.
And then we did some work to compute ages and to look at the overall dynamics of the region. So I think let's scroll down again. There might be something that I'm missing in between that we can hop on to for more discussion. But yeah, probably go a bit faster than this. Past the postage stamps, I think.
Okay.
Or actually, there might be something embedded in the postage stamps. Yeah, maybe here. Let's see. Yeah, a little bit up.
Oh, the discussion, the relationship is 5.1.
Yeah, 5.1's exactly where we should be. So yeah, I think we can loop back on this. Actually, I think we went too far. Isn't there another section before this?
Probably number 4.
Yeah. I think it's just because exactly.
Yeah, the cutouts.
It's because the figures are way further down compared to the
local
text.
environment.
Yes.
That's why. Yeah, exactly. So Circinus in the local environment. So I think let's just go straight down to the figures connected to these. So these are after all the posted stamps.
Right.
I think it's going to be like figure 14.
Okay.
So I think just go there.
It's there. Okay, 14. Let's go down to 14.
There we go. Exactly. So this so these figures basically show where or like the distribution of stars in the entire complex. So this is not looking just at stars connected to Circinus East and Circinus West. This is looking at the entire region.
I'm with you.
So Sir E and Sir West are groups 4 and 3 in the left panel of figure 14.
Okay.
So you can see that there are some stars there. It's definitely a substantial part of the population, but you've got this massive thing, which is group 8, which is ASCC 79. That's a large open cluster. And that alone contains about 500 solar masses of stars. And that's a bit of a low ball because, if we're going to be, you're more likely to be missing stars than, adding too many in here. So, and it also turns out that actually contains a 20 solar mass binary. Okay. So we got this like massive star driving a lot of radiation.
Yep.
And you can actually see that the velocities of the stars in the region actually follow a trend of, in the center of ACC 79, we have velocities that are, consistent with ACC 79. I mean, that's how things normally go. But as you go further out from that, you end up getting these nice gradients. So down towards the south and west in galactic coordinates, you end up getting exactly there. Towards group 5, we get this increase in velocity. And then same idea going towards the upper left, we get this steady increase in velocity.
Yes. Okay.
And you can see that the populations that are on the outsides of that gradient also have younger ages. So group 5 is younger than group 8, and group 6 and 7 are younger still in sequence with their distance from group 8. So 6 and 7 are sort of stacked. I can't remember which is the far one. I think it's group 6, but it's quite a bit further behind the other one. So it's actually quite a bit further away, and it's also quite a bit younger.
Okay.
So we've got this really nice sequence where as we go away from the central region, we get faster motion and we get younger populations.
Yes.
And
I'm with you.
And the way that we conceptualize this, and I go into a lot more depth on this in the paper that I write, sort of going into the solar content of Circinus. But it's essentially that, if you have a major star, like a big OB star, most likely an O star, driving radiation. What you end up getting is that, stars that form pretty early often form before there is much time to accelerate them all that much. So let's see, you have a bunch of stars that form in the center, you got a shell of gas around them.
Okay.
Well, as soon as that shell starts expanding into the gas, you're going to get some star formation right on the edges before those stars can accelerate that much.
I'm with you.
As the star formation progresses, you get a lot more, outlying bunches of gas that get more of this gentle acceleration. And that means that they're able to get up to higher speeds before they end up forming stars. You got a great simulation on how this works in my paper on the matter. But basically what this means, sorry, what's that?
Go ahead.
Oh, cool. Yeah. So basically what this means is that we've got this strong evidence for this feedback-driven sequential star formation or star formation sequence
Yes.
in
Yes.
Circinus, especially in this
Yes.
region around group 8. So that is groups 8, 5, 9, 7, 6.
Yes.
So all the stuff in that region. Right, exactly.
Mm-hmm.
Now, you notice that I didn't mention Circinus East or Circinus West in that.
Not yet.
However, there actually is a component of Circinus East that does follow that trend. So let's actually skip the next figure. I think it's figure 16 that we want now.
Let's go down to 16.
Yeah, there we go.
Yeah,
So
okay.
basically what I've done here is I plotted the expansion trend of the what we call Circe, so the Circinus central region. And so that's the trend of its expansion. If we just assume that these clouds follow those trends, it should be along that line, right?
Mm-hmm.
And what we see is that there's actually two distinct velocity components in Circinus East.
Very cool.
There is one towards the north, which goes from everywhere from 3 kilometers per second below the expansion trend to basically on it, and then Circinus East A, which is very different. So let's go back up to figure 15.
So I'm going to jump in here while you're scroll back up, but I'm just going to jump in meanwhile and point out that I think it was it Dobashi et al. Who noted that the CO gas also had multiple components. Do I have that reference correct, Ronan?
Yeah, I think it was Dobashi and Shimakura 2011, if I'm not mistaken.
Okay, yes.
Yeah.
And they saw different components in the gas.
CO. Okay.
Yeah, so CO gives the radial component, and then what we're seeing in Gaia is the tangential component traced by the stars.
Yes.
And you can see that there are two components in that transverse velocity as well. So you can see, just going down to Circinus East in the right panel of figure 14, you can see there's a bunch of velocities that are pretty low down there.
Yeah.
And then there are a few high velocities.
Yes, a little farther out.
Yeah. And where things get really interesting is when you look at how those are distributed on sky. So let's go down to figure 15.
Okay, that's 15. Ooh, this is good.
There we go. So you can see all the low velocities are right smack dab in the middle of Circinus East. And then the higher velocities. Oh no, left panel. Yeah. So we're talking like the like really low velocities in the sort of like cyan blue color. Yeah. So very low velocities right in the center there. That means that they have transverse motions that are almost identical to ASCC 79, which is the central cluster.
Yes, I'm with you.
And then, so we got this bunch of stars that follow that, and then you can see that there's this other component where we have consistent velocities coming down this way.
Yes.
Right. Yeah. And those are going directly away from the center, from the central population in ASCC 79.
Okay.
And what's really interesting here is that there's actually a velocity gradient across those stars. So if you just go back to figure 16 again.
Okay, down one. Okay.
Yeah, there we go. Yeah, so you can see there's this gradient, whereas some stars in the region have velocities consistent with the expansion of the central region.
Yes.
Some don't.
Yes.
So what we hypothesize might be happening here is that we know that there is a massive amount of radiation that is driving the acceleration of gas away from the central population.
Oh, great.
And it appears, based on the fact that there's this second component of Circinus East that has, much lower velocities, that there's sort of this other cloud that's sort of just in the area. It doesn't appear to be expanding with the rest of the Circinus region. So the proposal is essentially this.
Yes.
Gas comes from the central cluster, and it collides with an interloping cloud. And as the two chunks of gas start interacting, you end up getting star formation that has a range of velocities, ranging from velocities consistent with the material ejected from the central cluster, and gas with velocities consistent with that interloping cloud.
I'm with you.
And you can see that's exactly what we see here. You see that range going directly from the expansion line all the way down to the velocity of Circinus East A. And even moreover, if we just assume all those stars form at the same time, you can see that the stars that have the velocities that are higher relative to Circinus, relative to the central cluster, end up further away, which is consistent with, you start with everything
All right.
together,
Yes.
then the things with higher velocities move away. The ones that don't have that high velocity stay where they are. So what appears to be happening here is a signature of collision. This is exactly what Dabashi and Shimakura proposed in 2011, where
Okay.
you have this where you have this active collision that they saw in the CO.
Okay.
Uh, so it looks like we're replicating that pretty well here. Now
Cool.
we are lacking, some like radial velocities for some of these stars. We can't like
Okay.
directly tie it to the gas yet. But we can
Okay.
discuss that later on when we get into, what might come next.
Ooh.
But that's something we might want to do in the future.
Okay. Very nice.
Yeah, and we also did a little bit of discussion. So this works really well in the plane of the sky, but we also wanted to know, does this work out in terms of distance?
Yes.
And the answer to what was more or less. I mean, the error bars are pretty big, but Circinus East A and B have velocities that are very similar to each other. Or sorry, not velocities, distances that are very similar to each other.
Right.
So, that doesn't really, add much to what we're doing here, but what it does say is that it's consistent.
Yes. Yeah.
So it ends up, it doesn't refute what we're saying, essentially.
It's hanging in there. It's hanging in there. Very cool.
Yeah, exactly. So yeah, that's essentially the model we have for how star formation might have progressed here. And when you sort of like look at the morphologies of these two regions, you start to wonder, okay, why do we have this sort of very globular, blobby structure in the east, and you have this very filamentary, intricate structure in the west?
Right.
And we think that might be driven by this feedback-driven collision taking place in Sir East.
Okay. Yes.
Yeah, there we go. Exactly. That's the one.
Yeah.
So yeah. So you can see all the emission connected to the radiation from ASCT 79 up to the upper left of the central blob in Sir East.
Yes.
And then in Circinus West, it appears to be sort of more, it's further away, it's potentially sheltered by other gas in the region.
Oh.
So it appears to not have the same level of exposure to the broader environment
yet.
Yeah, although the distances to east and west are similar.
Mm-hmm.
Yeah.
And maybe there was some relationship. There's no direct relationship in terms in the kind of way that Ronan found for the sequence of star formation that's in the greater environment of Circinus East. It seems that didn't get to Circinus West.
Yeah.
Mm-hmm.
The question is, does it suppress star formation? Does it stimulate star formation?
What an interesting question.
So many fewer Herbig Haro objects. However, given the morphology, maybe it just mixes up the morphology such that we aren't seeing as many of those embedded stars.
Mm-hmm. Mm-hmm.
I'd like to point out, I'd like to point out these two images are very close to each other. In fact, they overlap. And just numerical zoom here, I'll just point out that this group of stars right here,
yes,
this group of stars right here. So these two images do barely overlap, and you can see that they are very close to each other, at least on the sky. And we do things spatially as well. So it is interesting how close they are to each other, and yet
it's so different.
And they have similar gas masses, if I recall correctly. So there's a lot of similarities between them. And so it is somewhat surprising how different they are.
It may be that Circinus East is protecting Circinus West from all this chaos.
Mm-hmm. Mm-hmm.
But there's a kind of I find this a little bit frustrating, and I need to think about this some more, but there's a kind of degeneracy between age of a region and morphology. And so, okay, lots of Herbig Haro objects. Is that younger, or is it simply that the morphology is permitting us to see more?
There you go.
A region with fewer could be younger, and there's some star formation starting, or is it just that they're hidden and it's older? So there's a few axes, But I think this kind of analysis that Ronan has applied to the greater region and the stars is very, very helpful. And then following up with CO
Yes.
measurement, and also refining Ronan's analysis by getting radial velocities for some of these stars really should be
Yeah,
possible.
yeah. Very cool.
Yeah,
Beautiful.
exactly. And we certainly do see a lot of cases where we have sort of like filamentary structures. I mentioned this a little bit early on, but like filamentary structures spanning, 30 to 50 parsecs. Those certainly exist in a lot of cases. So just because they aren't, directly interacting with each other doesn't mean doesn't mean they didn't form out of the same sort of preliminary, like, primordial structure.
Right.
So I think that's probably the most logical answer here is that, when you see things that are about the same age and the same rough area, Occam's razor is they probably have some relation to each other, but that doesn't necessarily mean that they are like actively interacting and affecting each other. Although, as we mentioned earlier on, there could be some like shielding of Circinus West by Circinus East that could be preserving a sort of more quiescent, calm environment in Circinus West. But we definitely need more data to be able to answer these questions thoroughly.
And we'll come to that.
Mm-hmm.
Go tax. Very cool. Beautiful work. Beautiful work. Beautiful images, beautiful distances. Very nice. Travis, Lisa, and Ronan, I want to thank you so much for walking us through your very awesome AJ paper. Very cool.
Thank you.
And
I want to call out those other authors on our paper, or students who worked with
please do. Please do. Give me a shout out.
Travis's students.
Shout out to Elsa and Kirk, who were instrumental in searching these images for the Herbig hair objects, which you don't really get conveyed in those figures, is how big they are. I mean, again, they're 520 megapixel, and we wanted to be certain we found everything. It's remarkable how good the human brain is at finding subtle changes.
We're good at that. We're good at that.
What's really fun about star-forming regions is that our brains are really well suited to interpreting them, just because we have all these visual cues that our brains can work with. And so the important thing, though, is our brains also fatigue. And so having students who are indefatigable to is critical. So it was important to have them part of the project.
And students, you will be here soon too. So very good. So all of you touched on it a little bit. And so let me push on it. And before I start that, let me just say I will put a link to this companion paper, the second one, 2025, in the description below the video. But you all touched on it, and there was even a section in there that we kind of punted on, and that's sort of where do we go from here, given the published article? Are there more images to take? We have some new telescopes coming up. Are those going to help some things? We talked about the radial distances and so on. And how do we deconvolve this degeneracy that was mentioned between morphology and age? And so let me ask, where do we go from here, given the published article?
Well, there's so many different directions. It's kind of chaotic, but,
it's fun. It's fun. It's a good thing.
It's a blast. Like we've had all these ideas, and I mentioned the CO, but the Tobashi and Shimakura, like the CO mapping cut off just above Circinus East, and I'm like, oh, is there more? Like, what is it like up into that extended Circinus region that Ronan's worked on? And then there's the radial velocities, and that's just Circinus. But Travis and I's this project is a whole bunch of different regions that we've been taking images of, including the Aquila Rift. We have mapped the entire Aquila Rift, which is 100,000 solar masses of gas, according to Tom Dame's CO survey of years ago. And not much known star formation in there, but we have found dozens and dozens of Herbig objects in the Aquila Rift. It is rife with star formation, but it's this enormous region. And then we've been looking at smaller regions, which are a little bit more manageable, where we have all these images. We have a bunch more that we would like to get with DECam, but we already have a ton. And so some of these smaller regions are Ronan's approach is applicable. So I'll let you two say something about
So maybe,
Yeah, sure.
so maybe we'll
I
go
think I'll
from,
actually.
go ahead.
Oh, sorry, what was that?
I was just going to say, so maybe we'll go from 2,000 known HHs to 20,000. Are we going to get an order of magnitude?
Yeah.
Not right away, but systematic narrowband surveys,
Hmm.
potential for that. We have, in a region where there was very few known, we have found about 100 of them in the Aquila
Exactly.
Rift. We've found about 50 more in Ophiuchus. And so most of the regions that we've searched, we have more than doubled the number known.
Uh-huh.
So that's what's exciting is these high resolution, deep all sky surveys start coming online. This is what we
Yeah.
can look to.
Okay. Sorry, Ronan, go ahead.
Yeah, no worries. I just wanted to sort of like get back on the topic of you know, yeah, getting more information about the gas in the region.
Yeah.
And we actually have like an active idea as to how we're going to do this. So this is the sort of thing that we sort of like we're pondering how we would do it for a while because there aren't actually a lot of telescopes in the north that can do this sort of science. Like we or sorry, in the south that can do this sort of science. So we've got ALMA, which is a great telescope, but the
Yeah.
problem is it's got a pretty small field of view. So if
Right.
we want to like map these large regions, doing it with ALMA is completely hopeless. It's just yeah,
Yeah.
exactly.
Raster scan, raster
It-
scan.
yeah, we're
No.
gonna like claim the entire ALMA telescope for a
For a
few
year.
months, and I think they probably wouldn't give us that time.
Oh, come on, Tack, be nice.
So basically, what we're looking at is using APEX, which is a telescope
Oh,
operated by the Max Planck Institute down in Chile,
yeah.
and
Yeah.
the deadline on that is Friday. So I gotta get continue working on that. Uh, but yeah, the concept is we want to map Circinus East, Circinus West, and also another population to the north that's connected to some of the like youngest populations in that sort of like central region.
Yes.
So you want to get a sense for the dynamical state of the gas there, how it's moving, whether it's consistent with the sort of expanding shell around the central cluster. And I also have a collaborator doing some really interesting work. His name is Jeremy Karam. He's at McMaster University in Hamilton, Ontario.
Okay.
And what he's able to do is actually take observations of young surfing regions and basically forward simulate them. So, I've got this gas, I've got these dynamics. Let's try to see if we can see how this would evolve in the future.
Yes.
So it's a really cool thing to be able to do. And the hope is essentially to see, we know we've got this big chunk of gas to the north of the central cluster. How is this going to evolve? Will it form stars? Will it form stars for the next 5 million years? Will it form stars for the next 15 million years?
Okay.
And I've actually got a student sort of like, analyzing a population with sort of a similar stellar mass to this.
Okay.
And she's got a 19 million year star formation history in this region.
No.
So,
Okay.
so we have some really fascinating regions that we might be able to tie
Fascinating.
this into. So I think it might end up being a really important sort of cornerstone in some of this work where we've got this nice environment where we know it well and it's relatively simple compared to a lot of other regions at least where we can do this sort of work. So I think it's very exciting.
Yeah. Very exciting. It's very cool. Be really exciting to see this develop over the next couple of years. All right.
Yeah, absolutely.
So maybe I'll have you back here in a little bit.
Sounds good to me.
That would be awesome. All right. Travis, Lisa, and Ronan, thank you so much again for walking us through your very lovely paper. And that'll do, everyone. And I hope this made your star formation astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you.
Bye.
Thank you.